Good morning, guys. So, what we are going to look in this class is Nyquist Stability Criterion. So, what are the basics for Nyquist Stability Criterion? What is the need for Nyquist Stability Criterion? So, that are the and the procedure. Okay. So, that are the things we are. These are the things which we are going to look in this class. Okay. So as you see here, f of s is equal to s minus uh, z1, s minus z2 up to s minus zm divided by s minus p1, s minus p2 up to s minus pn, where z are zeros and p are the poles. Okay, you can see here. Uh, okay, so we are considering a function like this. Okay, okay. So so as we know, S is equal to sigma plus j omega. This we have seen in earlier classes. So a real part is sigma and imaginary part is omega. Okay. So please, you have to note this, uh, which is in S domain. Okay. So S is equal to sigma plus j omega. This is in S domain. You have to note this. And afterwards, we are for f of s. For f of s, we are considering an equation like this. Okay. U plus jv. Okay. So if for s, this is the expression. Then for f of s, u is equal to u plus jv is the expression. Okay. So u is the real part and v is the imaginary part. Okay. Okay. So as you can see here, a function is analytic. So this function is analytic in the S-plane, provided the function and all its derivatives exist. Okay. So the points in the S-plane where the function or derivatives does not exist are called singular points. Okay. So this is an expression for this is a meaning for or explanation for analytic function. So a function is said to be analytic if its derivative exists. Uh, okay, the points where the derivative does not exist is known as singular points. Okay, so the basic thing is that we have to map this s and f of s. Okay, so we are considering two domains, s domain and f of s domain. Okay, so we are mapping the function, okay, in s domain and f of s domain, and you are comparing both these uh, expressions. Okay, so this is what we are doing. Okay, so as you can see here, uh, this figure 4.2, you can see s plane. What you are seeing in s plane is not the same as f of s plane. Okay, so s plane you can see here, it is in the uh, right plane, correct? So right half of the graph, you can see here, it is in the right half of the graph. Okay, so whereas in for a f of s plane, you can see here it is circling the origin. Okay, so what we are doing is this plane s plane, you have this area in the right half of the plane. So this is left half of the plane, this is right half of the plane. So you can see here in the right half of the graph. So that corresponding to that, if you plot in the f of s plane, you can see here this graph is encircling a point. Okay, so encircling a point, that point is origin. Okay, you should note this. Okay, so this is how you have to compare. Okay, so you have to plot in s plane and you have to plot in f of s plane, and for Nyquist criterion you have to look into f of s plane. Okay, so the Nyquist criterion is particularly dependent on f of s plane. So you predict the stability, or you calculate the stability using the plane in f of s domain. Okay, so this f of s plane is more important in Nyquist stability criterion. Okay. Okay, so you can see here, for the development of the Nyquist criterion, the exact shape of the contour. So this contour is a new term which we are introducing. This circle is known as contour. Okay, contour. Okay, it's not required by, but only the number of encirclements of the origin of f of plane is essential. Okay, so how many times this plane crosses the uh, or encircles the origin, this is important. Okay, so it may be like, if you, the graph maybe can be like this. Okay, so that is not an issue, but how many times, maybe if it encircles one more time. Okay, so this information is important, how many times it encircles the origin, in, rather than the shape of the contour. Shape of the contour is not important, but the number of times the contour encircles the origin is important. Okay, okay. So as I shown, just know what is, you should understand what is encirclement and what is enclosement. Okay, or if you can say a point is encircled, or a point is enclosed, then how can you say that? Okay, so you can see here, this encircled, a point is said to be encircled by a closed path if it is found inside the path. Okay, so figure 1 is encircled point. Okay, so as you can see here, this figure 1 shows the encircled point, which is point A. Okay, so point B is not encircled, correct? So this contour encircles this point A. Okay, whereas this point B lies outside this contour. Okay, so you can say the contour encircles point A, but it does not encircle point B. Okay, okay, then enclosed. Okay, what is enclosed? Any point or region is said to be enclosed by a closed path. Okay, if it is found to lie to the right of the path when the path is traversed in the prescribed direction. Okay, the shaded regions in figure 2 and figure 3 are the regions enclosed by the closed path. Okay, you can see here, this is the contour, this is the area enclosed. Okay, so you can see this is the contour and this is the area enclosed. So it is depending on the, okay, path of the contour and which prescribed direction you want to mention. Okay, so it depends on your definition. Okay, so you can say, if find the enclosed path, find the enclosed area outside the contour, then you can mention this. Find the area enclosed within the contour, then you can mention this. Okay, okay, and see here the point A is not enclosed by the closed path, but point B is enclosed with respect to figure 3. Okay, so this is figure 3. So point B is enclosed, so it will be good, it will be going like this. So point B is enclosed, but point A is not enclosed. Okay, okay. Next, these are some examples or common cases uh, which is important in Nyquist plot. As we saw in body plot, we saw what are the various terms, common terms which are appearing. This is some examples. We saw some examples for polar plot also. Okay, so the function f of s and the s-plane contour. Okay, so which is given, and the corresponding f of s plane contour is to be calculated. Okay, so this is some standard forms. You can see here. Here we are having two zeros on the right half of the s plane. So this is 1 0, this is 1 0, which is in the right half of the s plane. Okay, so when two zeros are on the right half of the s plane, then you can see here uh, the origin is encircled two times, correct? Okay, so this is a standard. So if in case of some gate questions or any one word questions, if you can see which case the question comes in, then you can directly tell, okay, at least how many times the origin is encircled. Okay, okay, so this is a case, and you can see here two poles are on the right half of the plane. Okay, so you can see here the direction of the this thing has changed. Okay, contour has changed. Okay, it is in anti-clockwise direction. So here it was in clockwise direction. Okay, so here it is in anti-clockwise direction. The contour is in anti-clockwise direction. You can see here using these arrows. Okay, so if this is the case, if you have 1 0 and two poles, so poles is marked by x and zeros is marked by dot. Okay, so this is the case. Okay, so you have two anti-clockwise and okay, two anti-clockwise direction. um, Sorry, you have a contour which is an anti-clockwise direction. There is only one encirclement of the origin. Okay, so this is a case. And again, if there are two zeros and one pole, then there is one encirclement of the origin in clockwise direction. Okay, then you can see here two zeros and two poles. Okay, so there is no encirclement of the origin. Okay, you can see here there is no encirclement of the origin. Origin is not encircled. Okay, so these are some common cases. We'll solve problems uh, regarding this later. First, we are understanding how, if there are two number of poles, how will be the contour. If there is two poles and two zeros, and how will be the contour. Okay, so this is what some common cases we are looking at. Okay, so as you can see here, poles are two poles are there, two poles and one zeros are there, but it's not in the S plane. Okay, so you can see the same case reappears, same result reappears, which is it does not encircle the origin. Okay, okay, so this is what okay, so this is what the common cases is. Okay, Okay, the summary of relationship between the enclosure of poles and zeros by the S-plane, closed contour, and the number of encirclements of the origin of f of S-plane by the corresponding f of S-plane contour are given below. Okay. Some common inferences they have given. If S-plane closed contour encloses Z number of zeros in the right half of the S-plane, then the corresponding contour in the S-plane, f of S-plane will encircle the origin of the S-plane Z times in the clockwise direction. Okay. So, if the S-plane encloses Z number of zeros in the right half of the S-plane, okay, in the right half of the S-plane, then the corresponding contour in the f of S-plane will encircle the origin Z times in clockwise direction. Okay. Okay, so easy to remember. If there are Z number of poles in the right half of the S-plane, okay, then the f of S plane, f of S contour encircle the origin of the f of S plane Z times in the clockwise direction. Okay, so only thing is this contour should have these zeros. Okay, so if S plane, second case, if the S plane closed contour encloses p number of poles in the right half of the S plane, okay, then the corresponding contour in the f of S plane will encircle the origin of the f of S plane p times in the anti-clockwise direction. Okay, so for zeros you have, depending on the number of zeros, you have encirclement of the origin in clockwise direction, and depending on the number of poles enclosed in the S contour, okay, in the right half of the S plane you have number of encirclements of the origin of f of S plane p times in anti-clockwise direction. So for Z you have clockwise direction, for poles you have anti-clockwise direction. Okay, so next, third case is if the S-plane closed contour encloses Z zeros and P poles in the right half of the S-plane. So you have both zeros and poles, and if P is greater than Z, if P is greater than Z, then obviously P, the effect of P will be greater, so you have anti-clockwise direction rotation. So number of times is P minus Z times. So it is easy to remember, and logic is good. Okay, so if S-plane closed contour encloses Z zeros and P poles on the right half of the S-plane. Okay, so the next case is both is present, Z zeros and P poles are present, and P is less than Z. Okay, then, okay, so obviously S will be, Z is greater, so the effect of Z will be more. So clockwise direction the encirclement is experienced. Okay, so number of times is Z minus P times. Okay, simple. Okay, next, if the S-plane closed contour encloses Z poles and P poles on the right half of the S-plane, and if P is equal to Z, okay, then, okay, then the corresponding contour of the S-plane will not encircle. Don't thus there will not be any encirclement. Okay, okay, if the S-plane closed contour does not enclose any pole or zero, so poles and zeros are there, but the S-plane contour does not enclose these poles and zeros, then the f of S-plane will not encircle the origin of the f of S-plane. Okay, so these are the six cases. Okay, so the six cases you should remember. If you remember, you can predict the contour very easily. Okay, okay, so finally, the relation between the enclosure of poles and zeros of f of s lying on the right half of the S-plane by the S-plane contour and the encirclements of the f of S-plane by the corresponding f of S-plane contour is called a principle of argument. Okay, so you're relating, okay, the S-plane and the f of S-plane. Okay, Okay, so so we have two planes, S plane and f of s plane. So S plane you are plotting the values. Okay, poles and zeros you are plotting, and you are developing the contour. Okay, in the S plane. So you are comparing this S plane with the f of s plane. Okay, so f of s, you have an expression u plus j in the format u plus jv. Okay, as you see, as you have seen earlier. Okay, if you convert this S plane to f of s plane, it and the stability is observed by the number of encirclements of the origin of f of s plane. Okay, okay, okay. So this relationship is known as principle of argument. Okay, okay. So the principle of argument is stated by this big definition. So as you can see here, let f of s is a single valued rational function and is analytic. Okay, in a given region in the S plane. Okay, except at some points. Okay, so analytic in the sense it is differentiable. Okay, um, now if an arbitrary closed contour is chosen in the S plane, so if you are considering an arbitrary closed contour in the S plane, so that f of s is analytic at every point on the closed contour in S plane. Okay, then the corresponding f of s plane contour mapped in the f of s plane will encircle the origin n times in anti-clockwise direction, where n is the difference between the number of poles and the number of zeros of f of s that are encircled by the chosen closed contour in the S plane. So first you just learn this, then we will, when we solve problems, we will understand better. Okay. Okay, so the general we are standardizing this 6 cases to a particular expression n. Okay, so n is equal to p minus z. So n is number of encirclement of origin of f of s plane made by the f of s contour. Okay, so okay, so z is the number of zeros of f of s lying on the right half of the s plane and enclosed by the s plane closed contour. Okay, p is the number of poles of the f of s lying on the right half of the S plane and enclosed by the S plane closed contour. Okay, so these are some conditions. Okay, so based on the value of n. Okay, so the value of n can be positive, 0 or negative. Okay, based on the sign of n, the following conclusions can be made provided the arbitrary S plane contour is chosen in the clockwise direction. So you are choosing a plane in the S domain. Okay, okay. So if n is positive, then the direction of encirclement of the origin of f of plane will be anti-clockwise. So you can say this. So n is positive in the sense p is greater than z. Okay, as you see, as you have seen in this um, third case, as you can see in this third case, p is greater than z, so anti-clockwise direction. So logically n is equal to p minus z. So if n is positive, number of poles is greater, so obviously the encirclement of the origin will be in anti-clockwise direction. So if n is 0, there will be no encirclement. That is in fifth case. That is fifth case. Okay, so n is negative, then the direction of encirclement of the origin will be in clockwise direction. Okay, so this is what we are generalizing the this case. Okay, so depending, we are introducing an expression, denotation n, which relates p and z. Okay, So depending on the value of n, you are predicting or you are calculating the encirclement. Okay. The same as this cases, there's no difference. Okay. 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 So what we have seen is we are learning through a new stability criterion, which is Nyquist Stability Criterion. Okay. So Nyquist Stability Criterion, what is the purpose? It is a famous predominant stability predicting method in when the system is analyzed in frequency domain. Okay. You have Routh Hurwitz stability criterion, which you have studied earlier. Okay, which we used for when the systems are analyzed in time domain. Okay, so that is for time domain. This stability technique is for frequency domain. Okay, so what we are doing in this thing is we are calculating the we are predicting the stability depending on the number of encirclements of the f of s contour. Okay, number of encirclements on and the direction of the encirclement. Okay. Okay, so that is how we are calculating the stability. Okay, using the contour of f of s. So to calculate f of s, we are starting from s domain. Okay, so we have studied s domain earlier, which is s is equal to sigma plus j omega. This we know earlier. Okay, so sigma is the uh, real part and omega is the imaginary part. Okay, so we are introducing another expression or another transfer function f of s. Okay, so f of s is equal to u plus jv. We are introducing u is a real part and b is the imaginary part. Okay. Okay, this we have studied earlier. So this is explain how we are. So what we plot in the j omega and sigma. This is not u. This is sigma actually. Okay, so I couldn't write on the screen. That happened. Okay, so j omega sigma. Uh, this contour which we which is dashed. Okay. So the corresponding f of s plane you can see here, it is converted into a contour which encircles the origin. Okay, so this is what we are doing. We are converting s plane into f of s plane, and you are calculating the stability depending on the encirclement. Okay, so then we have seen what is encirclement and what is enclosed. Okay, so this is the first figure 1, which says uh, the point A is encircled, okay, by the contour, while point B is not encircled. Okay, so the next figure 2 and figure 3 you can see here, on in both figure 2 and figure 3 the point A is encircled by the contour, but enclosed. How it is enclosed depends on the direction. Okay, so within the contour, so figure 2 is within the contour, figure 3 is uh, outside the contour. Okay, so figure 2 says the point A is enclosed. Okay, figure 3 says the point B is enclosed. Okay, then this table number 4, depending on the number of zeros and number of poles, we are standardizing the contour. Okay, if two zeros are there and it is enclosed in the S plane, as you can see here. Okay, then you have two contours two encirclements, sorry, a contour with two encirclements encircled in anti-clockwise, sorry, clockwise direction. Okay. So then two number of poles, second case is two poles in which you can see the two encirclements in anti-clockwise direction. So if so 1 0 and two poles, so poles are greater, so again anti-clockwise direction. So you can see two zeros and one pole, so it is in clockwise direction. Okay, so once encirclement. Okay, so if the poles and number of poles and the number of zeros are same, as you can see here. Okay, so there is no encirclement of the origin, and if the contour is not enclosed, as you can see here, the poles and zeros are lying outside the contour. Okay, so in that case also you can see there is no encirclement. Okay, so this is what they have given here. So this relationship between f of s plane and the s plane is known as principle of argument. Okay, so we are introducing denotation n is equal to p minus z. So p is the number of poles lying on the right half of the s plane, and z is the number of zeros lying on the right half of the s plane. Okay, so if n is positive, so p will be greater. Okay, since n is p minus z, p will be greater if n is positive, and so the encirclement will be in anticlockwise direction. If n is 0, so p will be equal to zeros, number of poles will be equal to 0, so there is no encirclement. So if n is negative, then the direction of encirclement will be in clockwise direction. Okay, so with this we will stop here. In the next class we will go into Nyquist plot and Nyquist stability